Let's take a look at where linear momentum came from, and then we'll see if we can come up with an angular momentum counterpart. If you remember, we started with Newton's second law. We used the definition of acceleration to change this into dv dt. We said if the mass is constant, we can bring it inside the derivative. And then we said, wait a minute, the net force is equal to the time rate of change of this quantity m times v. So if the net force is 0, m times v has to be constant in time. The derivative has to be 0. It has to be constant. So there's something special about this quantity. Let's call that momentum. And that's another form of Newton's second law. The net force is dp dt, the time rate of change of momentum. So if we start with that, and we do some mathematical manipulation, we go r cross f, r cross dp dt, and we get on the left side of that equation r cross f is the torque, or in this case it's the net torque. And we can bring the r inside of the derivative, and we get dt of r cross p. And so again, we say the same thing. We say if there's no net torque acting on our system, this quantity r cross p cannot change in time. It has to be constant. And that's our angular momentum. That's one form we have for calculating angular momentum. So what exactly is angular momentum? Well, let's think about linear momentum for a second. It's how hard it is to stop something that's moving. A lot of people call momentum inertia in motion, right? It's a combination of inertia, mass, and velocity. Angular momentum is how hard it is to stop something from spinning. And it's a combination of its rotational inertia and its rotational speed. So if something is spinning, it has angular momentum. Let's take a look at this example and what role angular momentum plays. This is a playground merry-go-round. It's a big rotating disc. Kids can jump on and off, and it rotates about an axis perpendicular to the ground through the center of the disc. If we look down from the top, a bird's eye view, the merry-go-round can rotate on its center point, and it can rotate one way or the other. If we have a kid over here running with some speed, and they run along and jump onto that merry-go-round and hold on, what's going to happen to our merry-go-round? It's going to start to rotate. And our kid will move with the merry-go-round, holding on. They will rotate together with some angular speed omega. So let's think about this problem for a second. What kind of problem is this? This is a collision. We had a kid running along and they collided with this merry-go-round. They are stuck together now. We know that we cannot get through that collision using energy because it's inelastic. These two objects stuck together. Inelastic collision. Our mechanical energy at the beginning is not going to be the same as the mechanical energy at the end. How about linear momentum? Can we use linear momentum to analyze this situation? No, we can't. At the beginning of our problem, the kid has linear momentum running along, and at the end, the kid doesn't have the same linear momentum. The kid's moving in a circular path. There's really not linear momentum to the right anymore, because the disc, the merry-go-round, is attached to the ground right there at that axle, attaching it to the ground. And so the ground got in the way, the earth got in the way, and we can't use momentum when the earth gets in the way. It basically has an infinite mass as far as we're concerned when kids and merry-go-rounds are involved. So linear momentum doesn't work, energy doesn't work. What lens will help us? Let's think about angular momentum. Angular momentum is conserved if there's no net torque. Well, if this axle is frictionless, if the disc can spin on that axle without any torque, then our system has no net torque acting on it. So angular momentum should be the same at the beginning and the end. So at the end, do we have angular momentum? We've got a disc with a kid on it spinning around. Yes, we said earlier that something that's spinning is going to have angular momentum, just like something that's moving in a straight line has linear momentum. Anything that's spinning or rotating has angular momentum. So we have angular momentum here. L final is not zero. And we said that there's no net torque acting on this system. So the initial momentum has to equal the final momentum. That means that L initial cannot be zero. Is the disc rotating initially? No, it was just stationary. We had a kid running in a straight line toward the disc. So a kid running in a straight line could have angular momentum if they can get something to rotate if they crash into it. So angular momentum is not just for objects that are spinning. An object moving in a straight line can have angular momentum if it can cause something to spin when it crashes into it. So in this example, our kid was running in a straight line, but because of their orientation with the disc, when they crashed into the disc, they got the disc to rotate. So the kid had to have angular momentum initially. Now let's take a look at a different example. I'm going to draw another kid. This will be kid A. And I'm going to draw another kid. I'll use green. And this kid runs really fast in this direction. And they run, jump, grab onto that merry-go-round. And what happens to our merry-go-round now? Absolutely nothing. When the kid jumps on here and grabs on, the merry-go-round does not move. The collision is in line with the axis of rotation. And so it can't cause our object to rotate. So in this case, the kid running in a straight line does not have angular momentum, because when it crashes into the disc, it can't cause it to rotate. It's aimed right at the axis of rotation. So let's take a closer look at our formula for angular momentum. We said earlier that angular momentum is equal to r cross p, where p is the linear momentum of our object. So let's take a closer look at that. This is the formula we use when we have an object moving in a straight line. So if I have an object here, mass m, moving with speed v, and I have an axis of rotation right here, this is my axis of rotation. Let's think about each one of these things. R is the vector that points from the axis of rotation to the location of my object. P is the momentum vector. that points in the direction of the velocity. R cross P is the magnitude of R times the magnitude of P times the sine of the angle you get when you put their tails together. So if this angle right here is phi, and I put their tails together, I'm going to move R. So now I've moved R up so that the tail of R and the tail of P are at the same place. So this angle is the angle I'm interested in, theta. And the sine of theta happens to be the same as the sine of 180 minus theta. And 180 minus theta is this angle right here. So I've got here R, the magnitude of R, the magnitude of P, and the sine of this angle. Well, what is R times the sine of that angle? R times the sine of this angle is this distance right here. I'm going to call this D perpendicular. The perpendicular distance from the line of the momentum to the axis of rotation. D perpendicular. So this is P times R sine of our angle, and I'm going to call that D perpendicular. So this is MV D perpendicular. Now this is a vector quantity, and I know that my angular momentum has to have a direction associated with it, and the cross product gives us that direction, R cross P. I put my fingers in the direction of R, I roll them toward P when their tails are together, and my thumb points into the page in this case. So for the example I just drew here, L would point into the page. In other words, it would cause something to rotate in the clockwise direction as I look down about this axis of rotation. If I had a big door attached here to this axis of rotation, and my object came along and hit it right here, it would cause it to rotate in the clockwise direction, or into the page if I use my right hand rule. So L is into the page for this object. It would cause something to rotate into the page if it struck it. What happens if my object isn't out here in front of my axis of rotation the way I drew it? What happens if my object continues on this path for a while and now it's over here, moving with speed v? I'll leave that as an exercise to you, but the angular momentum is exactly the same. It still has the same magnitude, and it still has the same direction. Why is it still into the page? Because if it crashes into something that's attached to that axis of rotation, let's say I have a big door here that sticks out like this, and my object crashes into it right here, what's it going to do? It's going to cause this door to rotate in the clockwise direction. It doesn't matter that it's past the axis of rotation now. So if you have an object moving in a straight line, our formula is R cross P. That's what we use to find the angular momentum of that object. And what does it turn out to be? It turns out to be the momentum of the object times the perpendicular distance from the line of the velocity to the axis of rotation. You have to have this perpendicular distance between the line of the velocity, that's this line right here, and the axis of rotation, that's this right here. You have to have that perpendicular distance. If the velocity is pointing right at the axis of rotation, then d perpendicular is 0. You draw a line, through this velocity, and it crashes right into the axis of rotation. It can't make something rotate if it crashes right into the axis of rotation. There has to be a perpendicular distance from the line of the velocity to the axis of rotation. And so that's why I think this is the easiest way to remember this. But it comes from r cross p. And this is the formula you use when you have an object moving in a straight line. And we already mentioned the fact that when an object is rotating, the angular momentum is going to be just like an object that's moving in a straight line for linear momentum. It's going to be a combination of inertia and velocity. For linear momentum, it's m, which is our inertia for an object moving in a straight line, multiplied by its velocity. For an object that's rotating, it's going to be its angular velocity and its rotational inertia. So the best way to calculate angular momentum, if it's an object that's spinning, it's I omega. If it's an object moving in a straight line, it's r cross p, which is the momentum, mv, times the perpendicular distance that the line of the velocity makes with the axis of rotation.